Hi, it's Paul Bamberg. Right at the end of the course back in 2015, I was pressed for time, and I don't think I did a very good job with the Lagrange multiplier proof. So here's another version of it. Here's the theorem. M is a manifold, and we've specified it as the locus of a continuously differentiable function, f of x equals 0. For example, x squared plus y squared plus z squared equals 1 specifies a sphere in R3. One of the requirements on this function is that its derivative is nowhere 0 on the manifold. So, think about the situation. We're talking about a manifold which could be a sphere, say the surface of the Earth. Now we've got another function, little f, also continuously differentiable. Let's think of that as temperature. What the theorem says is that if we consider a point in the manifold, i.e. a point on the surface of the Earth, it's a critical point of f restricted to m. That is, it's a critical point of temperature restricted just to points on the surface of the Earth. If and only if is what makes this proof tricky, there exists a Lagrange multiplier, traditionally called alpha, such that the derivative of little f, the derivative of the temperature function, is the multiplier lambda times the derivative of capital F. This version of the theorem is simpler than the one in Hubbard, since I'm imposing only a single constraint. That's a concession to that being the last proof in the course. Let's first do it the easy way. Think about the tangent space to the manifold M at C. Think of that as vectors that lie flat on the floor. They're tangent to the surface of the Earth at the point C. And we've earlier proved that this tangent space is equal to the kernel of the derivative of the constraint function. In other words, d capital F acting on V gives 0. We're assuming that a Lagrange multiplier exists, so d little f is a multiple of d capital F, and therefore when d little f acts on V, it also gives 0. In other words, df gives 0 on any vector in the tangent space to the manifold at point C, and that's precisely what we mean by a constrained critical point. There's a curious special case here. It's possible that f might have an unconstrained critical point at C. It could be, for example, that even if you went straight up or straight down into the Earth, the temperature would not start to change. The temperature would be an unconstrained maximum or minimum in R3. In that case, the derivative of f will give 0 on any vector, whether the vector's in the tangent space or not. d little f would also give 0 on a vector that went straight up or straight down. That's perfectly consistent with what we proved. In that case, the Lagrange multiplier is equal to 0, and d little f is the 0 Jacobian matrix. That's the condition for an unconstrained critical point. It's because of this possibility that you can't completely reverse the roles of the function that has the critical point and the function that specifies the manifold when you're doing Lagrange multiplier problems. Okay, now let's try it the hard way. First, I will do it as I did in the original lecture by contraposition, and this approach is consistent with the approach in the Hubbard's textbook. What we need to show is that the existence of a constrained critical point implies the existence of Lagrange multipliers. The contrapositive of that statement is that the non-existence of a Lagrange multiplier implies the non-existence, the absence of a constrained critical point. So what I'm going to assume is that there is no Lagrange multiplier. There's no lambda such that d little f is a multiple lambda of d capital F, or in other words, these two Jacobian matrices are linearly independent. One is not a multiple of the other. So we make a matrix whose top row is d capital F, the Hubbard's notation for that is alpha, and whose bottom row is beta equal to d little f. We're assuming these rows are linearly independent because no Lagrange multiplier exists, so this two-row matrix has rank 2. It has two linearly independent rows, and since it has rank 2, its image has dimension 2, and the vector 0, 1 is in the image of B. In other words, there's a vector on which the top row gives 0, d capital F on V equals 0, but the bottom row gives 1. D little f acting on V gives 1. So what have we got? We've got a vector that's in the kernel of d capital F. It's in the tangent space, but it's not in the kernel of d little f. And that violates the condition for a constrained critical point, because we know that the condition for a constrained critical point is that the kernel of d capital F must be a subspace of the kernel of d little f. If a vector is in the tangent space, it must also have the property that d little f acting on it gives 0. This proof actually generalizes quite nicely to the case where you have multiple constraints, even ones that are not linearly independent. And if you get seriously into this stuff, which will happen if you're an economist, you might want to look more carefully at the proof in the book, which covers this more general case. Here's another way of doing this proof. This is the version of the proof that Shlomo and Sternberg and I used in our textbook on Math for Students of Physics, and I actually like it slightly better. We've got just one constraint. We've got a manifold in Rn, and that manifold, because we have just one constraint, is a manifold of dimension n-1. Its tangent space has dimension n-1. So let's choose n-1 basis vectors in this tangent space. For each of them, d capital F gives 0, but we've got a constrained critical point, and by the condition for a constrained critical point, we know also that d little f acting on one of these basis vectors gives 0. Now, and this is the clever idea, choose any vector you like that's not in the tangent space. Since it's not in the tangent space to the manifold, it's not in the kernel of d capital F, and d capital F acting on this vector W gives 0. Sorry, is different from 0. Since it's different from 0, we can divide by it, and I'm going to set lambda equal to d little f acting on this vector divided by d capital F acting on the same vector. With this definition of lambda, you can mentally multiply through by d capital F, and you see that when you take d little f minus lambda times d capital F, that Jacobian matrix acting on the vector W gives 0. But, trivially, d little f minus lambda d capital F acting on any of the n-1 basis vectors in the tangent space also gives 0 for the simple reason that both these things give 0 when acting on V sub I. So, d little f minus lambda d capital F gives 0 on an n-vector basis for Rn, consisting of the n-1 vectors in the tangent space and the vector W, or, putting it differently, d little f is equal to lambda times d capital F, which proves the existence of a Lagrange multiplier. So, you might want to choose this version of the proof in preference to the one that I'd done earlier. Your choice.